Welcome to AI Paper Podcasts. Today we're doing a deep dive into a fascinating 2026 PhD dissertation from Claremont Graduate University. It's called Learning Without Training by Ryan O'Dowd.
Right, and this is a major one. For those of you wanting a quick summary, this paper fundamentally challenges the dominant machine learning paradigm of empirical risk minimization.
Yeah, the idea of using iterative optimization like stochastic gradient descent.
Exactly. Instead of hoping a neural network finds a solution through thousands of iterations, O'Dowd proposes using approximation theory and harmonic analysis to actually construct the solution mathematically in one shot.
And he makes three main contributions to get there. First, there's direct function approximation on manifolds, what he calls the sphere trick, which skips learning the manifold geometry first.
Second, he introduces a theoretical framework for local transfer learning, which lets you lift a function from a base space to a target space, even if you only have partial data.
And third is the MASC algorithm, which stands for Multiscale Active Super Resolution Classification. This completely reimagines classification as a signal separation problem rather than drawing decision boundaries.
The main hook here for you listening is that we are looking at replacing the black box of training with transparent mathematical operators.
All right, so that's the high-level view.
Right.
Let's really get into the weeds of this because the premise basically starts with a pretty heavy critique of where we are right now in ML.
Yeah, or at least where we've been stuck for the last decade or so. I mean, we're all very used to the standard supervised learning loop, right? You define your loss function, initialize some massive network, and you just run SGD until the error converges.
Right, the gradient descent religion. We just sort of assume that if we throw enough compute and enough data at it, the optimizer is going to eventually find the global minimum.
Got to find it eventually. But O'Dowd points out in his first chapter that this approach has these massive theoretical holes that we kind of gloss over them in practice.
Yeah.
The most glaring one is just the optimization problem itself. Like, we all know about local minima, but he highlights a really specific failure mode called dead on arrival networks.
Dead on arrival. I love that term. It sounds like a generic action movie, but in the context of machine learning, it's actually pretty terrifying.
Oh, it really is. It happens when you're trying to approximate a function, even a really simple one, say the absolute value of t, and just due to poor initialization, the gradients vanish immediately.
Right, so the network just outputs a constant value.
Exactly. It doesn't learn anything. It's just a brick.
So you have the right architecture, you have the data, but your search mechanism just completely fails before it even gets off the ground.
Precisely. And so O'Dowd's core argument is, why are we even searching? Like, we have these universal approximation theorems that tell us a neural network can represent the function.
But they don't tell you how to actually build it.
Right. They're existential theorems. They say, sure, the solution exists somewhere in this massive weight space, but they don't give you a constructive recipe to actually find those weights based on your data.
So he wants to move us from simply proving existence to actual construction.
That is the whole philosophy.
Yeah.
He wants to use data-driven mathematical operators to build the approximation directly. No iterations, no epochs, just math.
Which sounds amazing. And the first major tool he introduces to pull this off is in Chapter 2, which tackles approximation on manifolds.
Yes.
And this is where we really get into the manifold hypothesis. Just as a quick refresher for you guys listening, we generally assume that high-dimensional data, like, say, a 4K image, isn't actually filling up that entire high-dimensional pixel space.
Right. It lives on a lower dimensional structure.
Yeah.
A manifold that's embedded inside that larger ambient space.
Exactly. And the traditional way we handle this standard manifold learning is a two-step process. First, you have to actually learn the manifold. You run something like Laplacian eigenmaps or diffusion maps to figure out what that geometry is.
And then step 2, you build your function approximation on top of that learned structure.
Which, seems totally logical. Map out the territory first and then build the house.
It is logical, sure, but it's incredibly fragile. O'Dowd critiques this heavily because it basically compounds your errors. If your map from step 1 is noisy or distorted in any way, your function approximation in step 2 is just going to be garbage.
Not to mention, step 1 is expensive.
Hugely expensive.
Yeah.
Doing eigendecomposition on massive data matrices is not exactly lightweight compute.
So how does he actually get around doing that? The paper claims he achieves learning on manifolds without actually doing the manifold learning part.
Right, so this brings us to the sphere trick. He takes the data from the ambient space, let's call it RQ, and he just projects it directly onto a sphere of the same dimension.
Okay, but hang on. Isn't that just a massive distortion? If my data looks like a classic Swiss roll and I just smash it onto a sphere, haven't I completely destroyed the geometry I'm trying to leverage?
You would have, yes. If you were using global kernels, that would ruin everything.
Yeah.
But O'Dowd uses a localized kernel. It's constructed from spherical polynomials, somewhat related to Legendre polynomials.
So localized is the operative word here.
Very much so. Think of the kernel as a really tight spotlight. When you evaluate the function at a specific point, the kernel is only looking at data points that are its immediate neighbors on the sphere.
Oh, I see.
Because it's so tightly localized, it just ignores the global curvature completely.
Yeah.
It relied on the fundamental definition of a manifold, which is that locally, it always looks flat. It looks Euclidean.
So it literally doesn't matter if the global shape is a Swiss roll or a Klein bottle or whatever. Locally, it's flat, and the kernel just adapts to the local smoothness of the function on that specific flat patch.
Exactly. It implicitly uses the geometry without you ever having to explicitly calculate an atlas or a coordinate chart.
Yeah.
And the beauty of this is that it solves a massive problem in ML naturally, the out-of-sample extension problem.
Oh, absolutely. That's always the classic headache with things like diffusion maps. You train on your data set, and then a brand new data point comes in.
Right, and usually you have to restart the whole expensive process just to figure out where that one new point lives in your embedding.
But with his method...
With his method, the kernel is defined on the ambient sphere. The sphere is defined everywhere. So you get a new point, you just project it, apply the exact same mathematical formula, and you're done.
So it handles streaming data natively. That's huge. And he applies this to a real-world medical imaging problem in the paper, right? Magnetic resonance relaxometry.
Yes, and it's a perfect test case because it's a physics-based problem. They are trying to recover specific parameters from bi-exponential sums to measure myelin water fraction in the brain.
Right, myelin being the insulation on your nerves, which is incredibly crucial for tracking neurodegenerative diseases like MS.
Exactly. And the underlying math problem, recovering those decay rates, is notoriously ill-posed. It is hypersensitive to noise. If your signal-to-noise ratio drops even a bit, traditional methods just fall apart completely.
But O'Dowd's direct approximation method handled it.
Beautifully. He showed it could recover these parameters effectively, even with significant noise. But the really interesting part was how the error behaved compared to neural networks.
How is it different?
Well, he compared his approach to RBF radial basis function networks. The RBFs showed global error oscillations. It's known as the Gibbs phenomena.
Ah, so if there's a sharp change somewhere.
Right. If there was a singularity or a sharp jump in one part of the brain image, the error would ripple out and corrupt the prediction everywhere else in the image.
Whereas O'Dowd's method kept that error contained.
Entirely contained. Because of that tightly localized kernel, the error was restricted strictly to the singularities themselves. The rest of the approximation stayed perfectly clean. It's essentially the difference between using a surgical scalpel and swinging a sledgehammer.
That makes so much sense. And it segues perfectly into Chapter 3, which tackles local transfer learning. Now, normally when we talk about transfer learning and deep learning, we mean taking a massive ResNet trained on ImageNet, chopping off the final classification layer, and fine-tuning it on, say, chest x-rays.
Yeah, that's the standard engineering view. But O'Dowd takes a rigorous functional analysis view. He refers to it as lifting. You have a mathematical function on a base space, and you want to lift it to a target space.
And the example he uses here is neuroimaging again, specifically tracking Alzheimer's progression.
Right, so imagine you have a model of disease progression built on a healthy standard brain atlas. That's your base space. But your specific patient has severe atrophy. Their brain geometry is physically warped. It's different. That's your target space.
So you need to transfer the predictive function to this new deformed manifold.
Exactly. And the catch is, and this is why it's called local transfer, we might not have the full data for the patient. We might only have partial scans.
Which is super common in clinical settings.
Right. So O'Dowd develops this theoretical framework using what he calls a joint data space. And his main innovation here is a rigorous theoretical bound based on the concept of smoothness.
Smoothness is the key metric.
It is. The theory shows that if you know the smoothness of the function on the base space, which you do because you constructed it, you can mathematically predict exactly how much that smoothness will degrade during the lift to the target space.
So it's not just the usual ML approach of try it, wait for 3 days, and see if the validation loss goes down. It's actual math. It's saying, We can guarantee the performance within a certain margin based entirely on the underlying geometry.
And that kind of guarantee is exactly what is missing in so much of modern AI. We trade guarantees for massive scale. O'Dowd is showing us how to bring those guarantees back.
Which I think leaves us perfectly to what might be the most radical part of the entire dissertation. Chapter 4. The MASC algorithm, multi-scale active super-resolution classification. This is where he essentially tells us we've been doing classification entirely wrong this whole time.
Yeah, he completely reframes the problem. Think about standard classification SVMs, neural networks. It's always about finding a decision boundary. Where exactly is the line in high-dimensional space between a cat and a dog?
Right. And we spend millions of dollars in GPU compute time just hunting for that arbitrary line.
And O'Dowd says, just ignore the line. Look for the signal instead. He treats the data distribution as a mathematical measure, and the classes are treated as sources within that measure.
He compares it to point-source signal separation, right? Like de Prony's method.
Exactly like that. Think of it like trying to isolate specific radio frequencies from a really noisy broadcast. He wants to recover the supports, the core areas of the class distributions. And he achieves this with MASC, which is this incredibly efficient four-step process.
Let's walk through those steps because they're really intuitive. Step 1 is thresholding.
This is essentially a cleanup step. He uses that localized kernel we talked about to estimate the density of all the data points. If a point sits in a really low-density region, meaning it's almost certainly just noise or a weird outlier, he just tosses it out.
So he filters the signal before doing any actual classification work.
Right. Then we move to step 2, which is building a multi-scale graph.
Okay, so how does that work?
He builds a graph connecting data points that are within a certain defined distance of each other. Let's call that distance eta. This creates distinct clusters of data little dense islands of connectivity.
And this perfectly sets up step 3, which is the active learning component. And I have to say, this is the part I found really clever.
It's brilliant. Usually in active learning, you query the oracle, the human labeler, for the points where the model is most uncertain. The edge case is right near the boundary.
Right, the hardest points to classify.
Exactly. But O'Dowd does the exact opposite. He finds the modal point of each of those connected clusters.
The modal point being the point with the highest kernel density estimate, like the absolute peak of the mountain for that cluster.
Yes. He points to that specific highly representative point and asks the oracle, what is this? And once he gets the label, since it's the most representative point of that entire cluster, he just propagates that label to every other point in the island.
So instead of agonizing over the weird edge cases, he identifies the undeniable core of the class and just fills it in instantly.
But he still has to handle those edge cases, which is what step 4 is for, increment. He increases that distance parameter, eta 2, he scales it up, he zooms out.
And when you zoom out, those separate islands might start to merge together.
Exactly. And this is where the super resolution aspect comes in. If two islands merge, and they already share the same label, great, you keep propagating. But if a cat island suddenly merges with a dog island, the algorithm detects a conflict.
And it stops.
It stops propagating in that specific local region. It effectively identifies where the boundary is by seeing where the conflicts naturally occur, rather than trying to search for the boundary globally from the start. He calls it cautious propagation.
It's so elegant. And he tested this on hyperspectral imaging data sets, right? Salinas and Indian pines. These are heavy, dense, high-dimensional data sets. How did MASC actually compare to the state of the art?
He compared against LAND, which is learning by active nonlinear diffusion in LAND. MASC was highly competitive, sometimes slightly better on accuracy, but the real massive win was computational speed.
Because it's not doing that global diffusion across the whole graph.
Precisely. LAND requires computing diffusion distances across the entire dataset, which is wildly expensive. MASC relies entirely on those local kernel estimates. It's orders of magnitude faster to actually compute.
And there was also that synthetic benchmark he ran, the circle on ellipse data.
Ah, yes, a classic topological nightmare for classifiers. You have a circle of data points physically intersecting an ellipse of data points.
And those intersection points are where almost every standard classifier just chokes.
Right, because the boundary is ambiguous. But MASC handled the overlapping supports beautifully. The error was strictly localized to just the intersection points themselves. It didn't let the confusion at the boundary bleed out and corrupt the prediction for the rest of the clear circle or ellipse.
Which connects right back to his core constructive argument. MASC constructs the class support from the dense core outwards rather than trying to arbitrarily slice up the space with a hyperplane.
Exactly. And honestly, this has profound implications for how we view hyperparameters in general. I mean, think about deep learning today. Hyperparameters are basically magic numbers.
Total alchemy. We just tune learning rates and batch sizes until the loss curve looks pretty.
It is alchemy.
Yeah.
But in O'Dowd's framework, the parameters like n, which is the polynomial degree, and q, the manifold dimension, they are actual physical mathematical properties of the space.
They actually mean something tangible.
They mean something. The parameter n is literally your resolution bandwidth. Q is the geometric dimension of your data. Because they are grounded mathematical properties, you can derive strict error bounds.
Right.
You can confidently say, if I use bandwidth n, my error will be at most x. You simply cannot do that with a ResNet.
You really can't. And as we wrap up, in the conclusion of the dissertation, O'Dowd poses a thought that I think is going to stick with a lot of you listening. He suggests that deep neural networks might just be implicitly trying to learn the exact features that approximation theory handles explicitly.
A highly provocative question. We build these massive 100-layer networks, but why? Maybe layers 1 through 50 are just desperately trying to approximate that localized kernel. Maybe they're just struggling to learn the underlying manifold geometry via gradient descent.
So we are burning megawatts of power and millions of dollars to learn a geometry that we could have just projected mathematically in step 1.
That's the implication.
Mm-hmm.
He suggests that for physics-based problems, where the features are actual structural things like singularities or local smoothness, we might not actually need the deep part of deep learning.
Or at the very least, we shouldn't be relying on it to learn the geometry from scratch every single time.
Right.
So what's the practical takeaway for the ML engineer listening to this today? Do we all just go delete PyTorch?
No, definitely don't do that. But we might start looking seriously at hybrid architectures.
Yeah.
Imagine a pipeline where your very first layer is a fixed, non-trainable sphere trick projection.
Okay.
You use O'Dowd's math to handle the dimensionality reduction and the manifold alignment perfectly. And then you feed that clean, highly structured signal into a much smaller, shallower neural network to handle the final complex pattern matching.
Oh, I love that. You use the math for what it's inherently good at, structure and geometry, and the neural network for what it's good at, pattern matching.
Exactly. It's all about efficiency. And crucially, it's about reliability. If you can mathematically construct the solution, you know exactly why it works. If you just search for it with SGD, you just know that it works. Usually.
And usually is doing a lot of heavy lifting there.
Usually is perfectly fine if you're just generating funny cat pictures. It's absolutely not fine if you're doing medical diagnostics or autonomous driving.
Well, Ryan O'Dowd's dissertation certainly gives us a blueprint for a much more rigorous future in AI. Learning without training might sound like an absolute paradox at first, but it turns out it's just really, really good math.
It's a great reminder that before we had massive GPU clusters, we had theorems. And those theorems are still perfectly valid today.
They really are. I want to leave you with one final thought to mull over. In this paper, O'Dowd projects data onto a sphere because we have spherical harmonics. We understand the math of the sphere perfectly. But the sphere isn't the only mathematical shape we understand.
No, not at all.
What if we projected data onto other universal geometries? Like, what if we used hyperbolic space for highly hierarchical data, like tree structures or massive code bases?
Oh, that's interesting.
Right. If the core insight here is don't learn the manifold, just project onto a known geometry, then the entire existing library of geometric topology is basically just a catalog of potential new machine learning architectures waiting to be used.
That really is the next frontier. If we can correctly match the underlying data structure to the right projection space, we might be able to solve currently unsolvable problems without training a single weight.
Definitely something to think about while you're waiting for your next massive model to converge. Thanks for joining us on this deep dive.